Hey physicists, taking a look at our last lab on elastic energy, it looked like could use a little more review on the various forms of energy, transfer of energy, and particularly some of the calculations for elastic energy and spring force. So we'll take the opportunity today after the FCI to take a look at that. All right. Hey, so I want to give you the same experience that everyone else in physics has had. And take a look at this human slingshot in terms of elastic potential energy and elastic forces. Okay, in the video you can end up seeing that there is an ATV pulling people back, applying a force. Force times the distance means that we have some type of work being done. That work becomes energy stored in the elastic bungee cords. Okay. When it's released there, we can end up seeing that elastic potential energy turns into kinetic energy as they fly through the air. Okay. As they end up going the other side, okay, that kinetic energy slows them down, turning back into elastic potential energy. Now it is the nature of springs that as we pull them further back, we need more and more force to pull them. So what's interesting there is we end up seeing that even though they may be traveling at a constant velocity, the ATV has to exert more and more force on the rider. Hey, something else to notice as these people go flying along is where is their velocity the greatest? Okay, when they're pulled back, they have almost a zero velocity. As they head between the two poles, they continue to speed up. There we go. Okay. And then we get pulled all the way the other direction, over the river. We get stopped for a second, heading back between the poles. Okay, so as our elastic potential energy is depleted, we end up going into higher and higher kinetic energy. Here's an example. Okay. You can see they're traveling fastest between the poles. We see it here again. And then they stop when they're extended to the other side. Hey, a brief review with the idea of springs, their spring constant, and the force it requires to stretch a spring. And that relationship of the force of a spring is equal to this spring constant called spring constant K, and the amount that it's displaced from its equilibrium position is known as Hooke's law. You can see that expressed right here, that the force of a spring is equal to you'll see a minus sign, minus Kx. Don't worry too much about that minus sign. It's really just indicating that if I push on a spring, the force from the spring is in the opposite direction. Again, if I pull on a spring, let's say I pull it to the right, the spring is exerting a force on me to the left. That's the reason for the negative sign. Being careful in your pictures, you don't really have to worry too much about that negative sign. If I said, hey, what's the force on the spring, I would just drop the minus sign. And we see that over small ranges, Hooke's law is pretty linear. If I pull a spring back a certain amount, I'll have to exert a certain force F. If I pull it twice as much, remember this is the amount of stretch, it'll take twice the force. Okay. And that value K, just to be careful here, remember we use a sub K, let's say E sub K for kinetic energy. Please don't confuse the K that you see here, spring constant, with that value K. There are only 26 letters in the alphabet. Even when you go upper and lower case, it only gets us 52. We have a lot more variables in physics to express, so just be careful of that. K, when it's a high number, that's a strong spring, one that I might use, you can see down here, for an automotive spring. Okay, very light springs, let's say the inside of a watch or a ballpoint pen, have much lower numbers. So we can determine the value of K, the spring constant, from a single point, just looking at, if we know that F is equal to Kx, that also means that F over X being x being the amount it's stretched or compressed, is equal to k. If we want to get a better idea of that value of k, we can end up plotting all the points at various stretches and then seeing what the slope of that line is. You see that here, okay, that a spring has been stretched over various extensions, and then the force required to make that stretch is recorded. That straight line has a certain slope. Okay. Just like we saw before, the change in force over the change in x is equal to k. If we always went back to the origin, you can see pretty well that F over x is going to be equal to k. Hey, so what happens if I start to overstretch it? I got my slinky and it starts getting bent. That's where you start seeing this value here where it goes nonlinear. In real life, typically what happens if you start getting to this point where you have this nonlinear effect, if you were to let go of the spring would end up let's say getting shorter, but by the time it had zero force, it would be a little bit longer than initially, and you can see that in this deflection here. A little bit of spring engineering. Hey, quick look at the energy that's contained in a stretched or compressed spring. And we know that work, which is the transfer of energy, is force times distance. But what happens if that force does not stay the same over the distance that we stretch or compress our spring? And that's going to be largely the case. We end up with something that looks like this. As we increase the displacement, the force goes up. In fact, the slope of this line that forms the hypotenuse of this triangle is k. Okay, so we know that for some displacement x, the height of this triangle is going to be f, and it's going to be related by kx. We could do some substitution and find out that actually the area of this triangle, which is our measurement of energy, joules, remember it's precious, is actually 1/2 kx squared. And it's a nice expression for the elastic potential energy. So E sub PE is equal to 1/2 kx squared, where k is the spring constant, x is the amount of stretch in that spring, stretch from its equilibrium position. Hey, so a quantity that is consumed in a quantity that is conserved in nature is something that is the same, will be the same, and energy is like that. It may not stay the same in any one object. It may be transferred from one object to another, and we call that work. But in the entire universe, or in some collection of parts that does not do work or is not worked upon, will have the same amount of energy. We see that representation here, that we have our total energy is equal to our gravitational potential energy and our kinetic energy. And we have this new term here, our elastic potential energy, and now we have everything else, our dissipated energy. Up till a week or so ago, we combined that elastic potential energy was also dumped into dissipated energy. But now we have 1, 2, 3 different categories of energy, and then this thing that is the catch-all for everything else. Okay. So as we do these problems, as long as the system is not doing work or does not have work done on it, then we know that the total energy, E sub t, stays the same. It may change from one type to another. We see this most often gravitational back to kinetic, kinetic back to gravitational in a pendulum or a swing. Okay. In our lab that we did before, we saw some of this elastic potential energy turn into one of these other forms as soon as the elastic or the rubber band was sprung. Hey, the folks at the University of Colorado have a very nice simulation of a spring backing, a weight bouncing up and down on a spring, and each of the quantities of the various types of energy is plotted in the form of a bar graph, not really our pie chart like we've been doing. I'll leave the link here on the daily folder if you want to take a look at this for yourself, but I'll run a quick simulation right now. Hey, I'm going to briefly run this simulation. I hope it encourages you to go ahead and run this as well. Okay. Hey, so what I'm going to do is, right now I'm not interested in trying to plot friction here. And what I would like to do is take a look at our energy graph here. I go ahead and click this, and up along here we end up seeing a table where we have energy indicated by the vertical axis, and then the various types of energy. These are a little bit different than our normal. This is kinetic energy, gravitational potential, elastic potential, and thermal is what this simulation is calling all of that dissipated energy that we can't quite figure out what to do. So I've taken the friction, slid that down to none. It'll make it easier to study this. I'll put a 250-gram weight on here. Notice as I lift it, force times the distance, I'm doing work, and that's reflected here in our total energy. Okay. So I can end up taking this and release it. We'll see what happens. Okay. Yeah, as we expect that as this goes up and down, the total energy stays the same, but we end up seeing that kinetic energy changes a little bit, gravitational potential energy, and then the elastic energy in the spring also changes as a function of this going up and down. But take a look at the total energy, stays exactly the same. If I want to introduce a little bit of friction in this, okay, now let's see what happens. Okay. Notice the amplitude is getting. Okay, let's see what's happening here. Okay, so I think I'll disturb this a little bit. Okay, we have some friction now. Allow this to go up and down. And we can see over time that our thermal energy is getting greater and greater. Our total energy, because that consists of our kinetic energy, gravitational potential, elastic potential, and thermal, stays the same. But remember, this thermal stuff is not stuff that we can end up using very well. And maybe one last thing to notice is that as the weight goes up and down, our kinetic energy is going up and down. But notice when it actually, if you can watch this, I'll put it on maybe 16th speed. This is going much slower. Okay. Kinetic energy goes to 0 when this is fully stretched or compressed as it's going to be. There, stop there. Okay, we have 0 kinetic energy. It starts moving. We have kinetic energy again. So that's sometimes a clue. At the top of a toss, velocity is equal to 0. Kinetic energy is going to be equal to 0. Moving other objects around, when the velocity is 0, the kinetic energy is 0. Hey, last time we were together in class, we took a look at the various energies present when we had our bear fall out of a tree. Okay, we can, if you want to see a little more description, you can look here. You can scroll up on this Learn Lesson page if you want to watch the bear actually falling out of the tree. Okay, but we just checked off which various types of energy were present at these different positions before the bear falls, just as it's about to hit the trampoline, when the trampoline is fully stretched. Okay. This is just another way of presenting that information. I think of it as being the circle is the pizza. It's not going to get any bigger or smaller if we're just looking at energy. We're doing no work. Work is how we make that larger in the first place. Doing work on something else would be a way we make this smaller. But when we reviewed this in class, we made kind of check marks. So was there gravitational potential at this point? Was there kinetic? We're using these energy pies as being kind of another way of telling what type of energy is there. And we can see that before the bear falls in the tree, bear is not moving, trampoline is not stretched. It's all gravitational potential energy. As the bear falls, okay, and it's just about to hit the trampoline, we realize that the bear is getting lower to the earth, so we know that the gravitational potential energy has dropped down, but guess what most of that energy is turned into? Yeah, kinetic energy. If you want to follow this further, just go ahead and take a look at this link here. It'll be on the original document in my folder, or in the daily folder. Hey, the background document that I'm looking at here is the topic for Cycle 2 Learn Lesson. This will also be in schools if you want to go through this. But there's a sample problem here talking about, okay, we have an archer pulling a bow back. Oh, hey, that's spring energy. Releasing it toward a target and analyzing the energy as it moved throughout the system here. Okay, so take a look at this if you need help. I want to introduce the homework problems before I run out of time. Hey, so from the Learn Lesson, the problems you'll be doing are, let's scroll on over here. Okay, on the elastic energy problems, go ahead and open that up. Okay. You can see the problems here are the same ones that you'll find in the Learn Lesson itself, and this one only goes up till problem 7. Okay, the other ones 8 and 9 present some challenging issues that we have not looked at yet. Okay, so these are fill in the blank. Just worry about the number as listed here. Don't worry about the units. All right, hey, and enjoy the day. Hey, and so just one last note. Remember, our trebuchet final Performance will be next Wednesday, not Monday as originally stated, but we have a full rotation Monday, so we'll need the time on Wednesday.